Welcome to the Explainer. Today, we're doing a purely technical teardown of agentic infrastructure. We are completely stepping away from the marketing hype today to objectively look at the actual systems architectures that allow large language models to function as autonomous agents. We'll be drawing on some comprehensive deep research reports to explore the precise mechanics of context management, tool execution, and state persistence. So let's just dive right into this. All right, here is our roadmap for today. First, agentic harness architecture. 2. Automated harness evolution. 3. RAG versus stateful wikis. 4. The open knowledge format. 5. Related architectural paradigms. And 6. We'll wrap up with a technical summary. Starting off with Section 1, Agentic Harness Architecture. So what exactly is an agentic harness? Well, from a strict systems engineering perspective, it's defined as the deterministic software infrastructure, the middleware layer, and the execution runtime that wraps entirely around a probabilistic foundation model. Basically, the harness sits directly between the model and the real or virtual world, is strictly separate from the cognitive model itself, and it's also completely independent of the presentation layer or UI. It actually really helps to think of the foundation model like a CPU. It provides that raw, probabilistic processing power, the linguistic interpretation and the initial tool selection. But by default, that model is stateless. The harness, on the other hand, acts like your operating system. It's the cybernetic governor. It regulates the deterministic execution, manages state transitions, and enforces sandbox control. So if the model decides what to do, the harness controls exactly how it gets done, safely and reliably. Now, a production-grade harness pulls this off using 4 primary subsystems. First up, the interface and ingress layer, which ingests the actual tasks. Second is the session and state management layer. This is absolutely crucial because it persists your checkpoints over time. Third, we have the tool integration layer, which handles schema validations and execution drivers. And finally, the verification and guardrail layer. Think of this as your automated quality gate. It uses deterministic sensors like unit tests, linters, and static analyzers to validate the agent's actions before they're actually committed. Moving right along to Section 2, Automated Harness Evolution. Which brings us to Agentic Harness Engineering, or AHE for short. AHE is an open observability system designed to automatically evolve harness components, things like system prompts, tool descriptions, and middleware, all while keeping the base model entirely fixed. But to keep this from collapsing into just blind trial and error, AHE relies on 3 really strict pillars. First, component observability, meaning every single element is a Git-tracked, revertible file. Next, experience observability, which distills millions of raw trace tokens into structured, layered reports. And lastly, decision observability, ensuring that every proposed edit carries a mathematically falsifiable prediction. So how does this actually run in practice? Well, an overarching evolution agent executes a very strict 5-step deterministic loop. 1. It observes deep telemetry from executions. 2. It diagnoses failures by attributing them to specific harness components. 3. It proposes candidate revisions. 4. It evaluates those revisions using deterministic sensors on held-out tasks. And 5. It promotes only the mutations that demonstrably improve reliability without regressing on any previously solved cases. Section 3. RAG versus stateful wikis. We really have to talk about the massive contrast in efficiency here. The traditional architecture we all know, retrieval augmented generation, or RAG, is inherently stateless and, frankly, amnesic. It initializes from a 0 state on every single query, which forces the model to repeatedly reread and rederive knowledge from raw, disjointed chunks. That creates incredibly high latency. The alternative to this is the compiled LM Wiki, pioneered by AI researchers like Andrej Karpathy. This paradigm treats knowledge management like software compilation. The agent proactively compiles raw texts into a persistent, cross-linked Markdown wiki. Essentially, you compile once and you query continuously. To preserve data integrity and stop the system from turning into a chaotic mess, the agentic wiki requires a strict 3-layer topology with very clear ownership boundaries. At the very base, you have the raw data layer. These are your immutable PDFs, text files, and data sets that serve as a permanent audit trail. Sitting above that is the wiki layer. This is the mutable markdown that the AI agent alone generates, cross-links, and maintains. And finally, the schema layer, which holds static configuration files that give the agent its formatting rules, page specs, and operational instructions. Maintaining this whole topology relies on 3 core operations that the agent executes. During the ingest phase, the agent reads a new immutable source and compiles updates across multiple related concept pages over in the wiki layer. Then, during the query phase, it navigates that compiled index to synthesize answers directly from the highly organized markdown. And this is crucial. During the lint phase, it runs automated health checks to detect contradictions, orphan pages, or broken links, actively guarding the knowledge graph to keep it healthy. All right, Section 4, the open knowledge format. As more development teams started building their own bespoke wikis, Google Cloud realized there was a massive need for interoperability. So they introduced the open knowledge format, or OKF. The v0.1 specification is deliberately very minimal. It basically represents knowledge as a directory of markdown files. Each file just needs some minimal YAML front matter, specifically an explicit type field. The body itself is free-form markdown, using standard cross-linking. It also reserves index.md and log.md files for progressive disclosure and chronological tracking. OKF is great because it achieves structural interoperability without forcing a rigid semantic taxonomy onto your entire enterprise. Looking at this comparative analysis, the architectural trade-offs become pretty obvious. Now, stateless RAG scales highly based on database size, sure, but it carries a super high hallucination risk per query because of its isolation. A local compiled wiki is incredibly cheap, but bounded by context windows, and it can accidentally bake errors right into its notes. Google's OKF standardizes that markdown approach for better portability, but if we are talking true enterprise scale, architectures like the stateful typed graph replace flat markdown files with ACID-compliant transactional databases like Ipsila Semantic Graph. They use explicit typed edges, giving you robust role-based access control and allowing concurrent agent operations that are completely free of data collision. Section 5. Related architectural paradigms. Obviously, the systems we've been discussing don't operate in a vacuum. The infrastructure ecosystem out there is already highly specialized. Execution runtimes, like the open-source OpenHarness, give you local developer pipelines with built-in tool registries. Collaborative runtimes, like Semacroc, govern complex multi-agent professional workspaces. Then you have evaluation engines, such as the UK AISI's Inspect framework, handling large-scale safety benchmarking. And finally, observability platforms like Arise and Langfuse, which capture all that trace tree analysis and telemetry required for the evolution agents we talked about earlier. And finally, Section 6, Technical Summary. If you are planning on deploying agentic knowledge layers, the research highlights 3 absolute must-follow strategic directives. First, avoid the migration fantasy. Seriously, do not just dump thousands of unread PDFs into a new system. Seed the wiki gradually to let the model build a structurally sound conceptual graph. Second, enforce structural standardization. Use vendor-neutral flat file standards like OKF so your knowledge actually remains portable. And third, implement dynamic memory lifecycles. At a certain scale, static folders just become pure noise. You have to use confidence decay algorithms or explicit supersession via Git to maintain the integrity of your active search space. So, looking at everything we've covered, it's pretty clear that the true bottleneck for autonomous agents is no longer the foundational model's reasoning capacity. It's the structural integrity of the harness surrounding it. This shift from transient search to compounding compilation is fundamentally changing systems architecture. Which leaves us with a final, highly analytical question for your engineering teams. Is your enterprise infrastructure ready to refactor from stateless probabilistic queries to deterministic, compiled context execution? Thank you for joining me for this explainer.